So I'm Jukka Lehtosalo, and I've written a few PEPs. I work on Mypyc and Mypyc. I'm a TypeShot co-founder, and I'm a staff engineer at Dropbox. But really, actually my slides, can I get my slides visible? Yeah, this is really a dawn of a new era. I think things are not as they used to be. Something is in the air. Hardware prices are going up, not down. Like, what's going on? Like, CPU prices are going up. RAM prices have been spiking. The world is going crazy. But I think there's a silver lining in all of this. Making code faster is actually becoming important again. The lost art of optimizing your code is making a comeback, right? And free threading, which was just kind of released fairly recently, is one of the tools that can use to make your code much faster and avoid like buying this overpriced new hardware. Get more out of your existing CPU, memory, and data centers, whatever. So, free threading, I'm not going to go into too much detail, but basically, traditionally, Python has had the global interpreter lock, which means that only one thread can do any kind of CPU kind of intensive computation at any given time in one process. So if you have 3 threads that try to compute a bunch of stuff, it's going to take a long time for them to finish. So one of them do one at a time. But on a free-threaded Python, so this is a separate build. It's not enabled by default, so you have to install it separately. Starting from 3.13, you can actually use all your CPUs or cores on your hardware. And in this case, ideally, you could get like 3x the performance. Of course, in reality, it's quite not as nice. But anyway, this looks pretty promising. And of course, you've been able to do it for a long time. So multiprocessing has been around for many years. But free threading has some pretty key improvements. So first, it's easy and efficient to share objects between threads. And you can pass objects from one thread to another without like using pickle or anything kind of expensive. You have access to fast synchronization primitives. So you can do like really fine-grained kind of concurrency. Free threading can reduce your memory use because you share objects between threads efficiently. And also, you can share like module state and systems module, including like function objects, type objects, which in a large application can take like hundreds of megabytes of memory. And with multiprocessing, it's multiplied by the number of processes. And also, the program starts faster because you only need to do the initialization once. Of course, there's always a trade-off. So it's not just all good. So getting the like 3x or whatever improvement you want in performance is actually not quite as trivial as you might think. With threads, you have to debug race conditions that can be really, really complicated. And with multiprocessing, it's generally kind of easier to reason about these things. Not every third-party library supports free threading yet, though it's been improving quite rapidly. So I think that problem will go away. But right now, you might not be able to use all your favorite libraries. And also, you get a small, but still, it can be significant performance hit when you switch to the free threading build. So if you don't use threads at all, then you kind of lose some performance. The other way you can improve the performance of your Python code, like without having to do any like real work, right? Just kind of, you want to have a tool that you can like magically make your code faster, right? So Mypyc compiler is kind of not quite there, but almost. So this is a tool that's ahead of time compiler that compiles type-annotated Python, or if you want to get performance, you should have types, to fast C extensions. So the performance benefit you get kind of varies a lot depending on what you're doing and how you've written your code. But usually it's like something like 1.5x to 10x. And if you want more than, say, 5x, you probably have to tune and optimize your code a little bit. You can just write your regular Python, as you've been doing all these years. Mypyc is kind of mostly Python compatible in a way that any code that you compile with Mypyc is generally going to run just fine as a normal interpreted program. But if you are migrating your existing code to Mypyc, you probably have to tweak things a little bit. So it's kind of, there are a bunch of kind of significant differences that is good to know about. But usually the migration can be pretty smooth, but yeah, not always. And you can integrate compiled and non-compiled modules seamlessly. So you can call like share objects between like compiled and non-compiled modules freely. It kind of happens transparently. I guess the main drawback you should be aware of, Mypyc, when on free-threaded Python, we can't make the same thread safety guarantees that Python does. Like basically, like you can corrupt your memory. Mypyc kind of, that would, in the Mypyc context, like memory safety would be super expensive and super difficult to have. So we say like, hey, you have to use your logs correctly. Like, you know, like wash your teeth and stuff like that. So, so this is kind of something to keep in mind. Okay, let's start with a small example, just to get started. So Mypyc is shipped with Mypy, so it's kind of effectively part of the same project. You also need to install setup tools. And then let's start with this super simple like micro benchmark, the kind of a classic one. Recursive Fibonacci, right? Exciting. And okay, you run it on like regular Python program. Sure, it takes like, 1 second. Okay, that's kind of slow, right? When you use Mypyc, you have to compile it. There's a compilation step. But it's 10x faster. Yeah, amazing. Right, like, what can we do with all this kind of Fibonacci power? One of the things to know about is that Python doesn't let you run a C extension directly, so you kind of have to do like Python-C import something dance, or you need to have like a regular uncompiled Python kind of main program that you run, or something like that. So it's kind of just something to keep in mind. And on macOS, like when you compile stuff, then the first time you run it, it's kind of slow because it does some one-time sort of security check, whatever. So that's kind of just another thing to keep in mind. The first impression counts. Okay, this is a bit of history and kind of status. So Mypyc was originally built just to make Mypy faster, because Mypy was, back in the day, it was pretty slow. And so we get up to 4x speedup, and even on 3.14, which has been optimized, we are still getting a 4x speedup because we're improving Mypyc at the same rate as kind of Python has been getting faster, like interpreted Python. And since last year, we've been really focusing on getting Mypyc useful for non-Mypy use cases. We're trying to make it like really general purpose, that there's a large class of programs and problems where it can make your code significantly faster. And it's used by the Black source formatter and some other kind of open source project, also shipping wheels built with Mypyc. And at Dropbox, we've been compiling our like expensive, like commonly used shared libraries across hundreds of Python services using Mypyc. We can get like pretty measurable performance improvements in line with kind of the expectations that I gave you. And with this kind of progress, it's still kind of, it's only like starting, we are kind of going to continue a long time. And keep in mind that Mypyc, especially free-threading mode, is kind of still somewhat experimental. So yeah, it's kind of stable for Mypy, but other use cases are still kind of, developing gradually, like rapidly, and things are still changing quite a lot. Okay, let's like pause a little bit. So free threading, if you have like 5 threads, you might potentially get like 5x speedup, or like if you have 20 threads, like who knows? With Mypyc, you could get another 5x speedup. So now the obvious question everybody probably has at this point, like why not use both? Like what will happen if you use both, right? And that's what we are going to investigate. And I'm going to use a few code examples that are kind of try to mimic some real-world use cases that you might encounter in the world, and that kind of have similar like challenges, similar bottlenecks, but are kind of tiny, so I can actually talk about them in like the space of a talk. And I'm gonna identify the bottlenecks here and kind of see like how fast can we make these things go. Okay, let's start with this amazing program that will calculate an approximation of the value of pi. So this is using a Monte Carlo method, where we take like a random point in the unit square, and we check whether it's within the unit circle, and then based on that, we gotta get the fraction of points within and outside, and then from that kind of we can calculate it. That's kind of pretty cool math, right? Yep, and yeah, that looks good. We should be able to make it faster, right? And if we do it in a multi-threaded context, this example and all other examples, I'm going to use a thread pool executor from concurrent futures, which basically you can call the same function like many times across any number of threads, and then it kind of collects the results together. This is a really handy way to kind of run your stuff using multiple threads. And then in this case, we just take the like average of the results, and we get kind of better estimate the more threads we throw at it. And of course, like you have to use the free-threaded build, otherwise this kind of thread pool executor is kind of pointless if you're doing CPU-intensive work. Okay, actually, yeah, if we just run the example in multiple threads, actually it doesn't kind of get any faster in not any significant way. Anyway, so what's going on here? So we are calling random.random, which uses a global like random number generator object behind the scenes. And then when you call it, it kind of takes a log, and then it kind of calculates the number and then returns. So basically, because this is kind of slow operation relative to the others, maybe, what happens is that we are just waiting for the log. All the threads are competing for this log. So we can't really get any benefit. And this is kind of like something like this happens quite a lot when you're writing like multi-threaded code, especially if you want to like parallelize something. But luckily, this is kind of easy to fix if you like know how to, right? We just generate like separate random number generator in each thread. So you have like a thread local, and then they can't access the other one, so there's like kind of contention, and this should be much better. Right? Let's see. Wow! On a 16-core machine, this goes like 16 times faster. That's kind of pretty much linear. Kind of amazing, actually. And yeah, and this is like interpreted. This is kind of just normal Python. Yep, I like that. But, well, let's see Mypyc. Can we do even better? Like, hopefully, yes. Yes, and in this case, because we are spending most of the CPU in standard library module random, and Mypyc only compiles the file that you're compiling. It does, like all the standard library stuff is kind of still doing whatever it normally does, so it doesn't get any faster. So in this case, we still have an option. Mypyc has a kind of own standard library, libRT, which has some, it's not like a replacement for the Python standard library, it's more like a replacement for common performance bottlenecks and things where we can do better than the standard library for various reasons. And for example, we have an alternative to the random module there, which is faster when using Mypyc. It can also be faster when using interpreted Python. And yep, it's Mypyc optimized, and so that will kind of help us work around the standard library bottleneck. And also Mypyc, just to explain what's going on, these floating point values are compiled into like C doubles. It just, there's no like Python object created at all. So the random like function will return like a C float for you. And similarly, when we have this like math on floats, it just all kind of C floats or doubles actually all the way down. So they should be pretty fast. And actually, it is pretty fast. So sequentially, when you run on one thread, it's like 5x faster than interpret it on a single thread. And amazingly, when you're running on like 32 threads on a 16-core machine, it's like 82 times faster. So this is probably about the best you can like reasonably get with Mypyc and free threading. Yep, I'll take that. Okay, here's the second example. So we do something different. So we have a binary log file. So if you want to process a lot of data, like binaries like generally should be much faster than text, right? But with Python, it's not always the case, because Python kind of, you have to use the struct module, or that's kind of the common way to process binary data. So we're like 64-bit like timestamp, and then we have an integer user ID, and then we have a string, which is length, and UTF-8 encoded bytes. So these like each entry is like log entry is like that, and we want to find all the entries related to particular user ID. So we just get a bunch of entries as one huge bytes object that we read from a file. So that reading the file is included kind of in this program, but I'm not showing it. And then we just unpack it, each entry, and kind of get the variable length data, and then produce the results in a list of tuples with timestamps and decoded string. So this is kind of things, similar things kind of, you're going to come up quite often. But now I need to give you some background information. This is kind of a little tricky. So reference counting in free threading is kind of interesting. That since each object has a reference count, and when you like create a new reference, you increment the count. But this is basically like global state. What if you have an object that's shared between multiple threads, and they kind of each access, even if they do read-only access, they still increment and decrement the reference count and then causes contention. So in this small example, we have a loop where we just read the attribute to a local variable, and that produces a new reference, right? And then if you have like multiple threads running this loop, they all try to access the same reference count, and there's contention, and then again, like the performance might be really bad. So anyway, there are many ways you can kind of attack this. You can just try to use the same reference. So instead of creating like one reference per like iteration, you can do like same reference. You can do a thread local object, like we did in the previous example. But on the other hand, like one of the benefits of free threading is you can share objects. If everything needs to be thread local, it's kind of pointless. You could just use multi-processing, right? So, yep, this is kind of a tricky subject. So, okay, look at the code a little bit. So somewhere here is, I can kind of give a hint, there's a reference counting bottleneck, but it's kind of maybe not obvious what's going on. So, okay, that's kind of the secret. So what's going on here? This is kind of subtle. So entry is a global kind of struct definition, and when we call entry.unpack, we have to read entry from the kind of global namespace. And that's, I'm not like 100%, but my strong belief that it's, when you read from the globals, you kind of create a temporary reference, you increment it, and then you get this bottleneck. But it's kind of difficult to reason about. So anyway, based on that hypothesis, we can try to fix it. So we'll take a local reference to entry outside of the loop. So you have like create one reference, and we reuse the same reference across each iteration. And let's see what happens. So that's actually, yeah, that solved the problem. Now we can actually see it scale. So this is actually, yeah, 12x faster on 16 cores. So that is, yeah, that is pretty good. Okay, what about then Mypyc? In this case, again, this is not a case, kind of the common theme here, because when you have trouble with Mypyc, often it's a problem that you're spending time in the standard library or some third-party library, so even if you code that you compile codes like 100 times faster, if you spend all the time in the standard library, it doesn't really help you much. Okay, in this case, yeah, we have a kind of replacement for struct in Mypyc. It's kind of lower level. It has like functions to read and write binary data from a bytes object, basically, or like the writing is a little different, but anyway, you get the idea. So we just replace the struct with a bunch of read functions, but otherwise it's kind of similar. It's not that much complicated. You just need to keep track of the index yourself. And actually, this makes things much, much faster, because also we don't need to generate like any kind of There's no like object creation, anything. It's all kind of happening as quick, low-level C operations. So this is 24 times faster in one sequential, and when you're doing free threading, it's 51 times faster. In this case, if you use like 32 threads, it's actually worse. So in this case, we hit some other bottleneck. I suspect it's probably like memory bandwidth, because we're reading so many files in parallel, and then we're kind of hitting cache, kind of running out of cache space, whatever. So like using 8 threads is actually about optimal on this piece of hardware. But on my like laptop, it's different, so it kind of scales better because it's probably small memory bandwidth. So yeah, you have to tweak things a little bit to get the maximal performance. Final example is a route finder. So basically it finds the shortest path in a map. So it's kind of like, like Google Maps style thing, but way simplified. And this is a bit more complicated, so I'm not going to show the whole code. But anyway, this is sort of a general idea. So we have used the Dijkstra's algorithm. It's kind of from the textbook. If you've done a computer science intro to algos, it's probably there. You don't need to remember how it works exactly. And then we calculate like many routes in parallel. So multiple threads each kind of calculating an independent route. So it's more like you have like service and multiple users are like asking for routes. So then we can, and we also return a bunch of alternative routes, like the shortest path, and then a couple of alternative routes in case you want to take like a detour or you don't want to avoid this particular road or something. They're kind of like Google Maps. And then we share the graph. Because if you have like the whole like one city or country or whatever, you don't want to have like 20 processes each with the whole map in memory. So yeah, you can share the graph, which is pretty nice. Here, I introduced a new concept. It's another like liberty feature, which kind of helps make your code faster. This is like an array-like, grail array-like type, which is optimized for Mypyc. You can use it instead of like list or tuple or like a rated array. You can use the packed representations kind of transparently. So if you use I32 as the item type, which is like 32-bit integer, then each item is like only 4 bytes, whereas like if you have an int object, it's something like, I don't know, 50 bytes each. So that's way more expensive. And you can also put like reference type, and you can do nested effects as well. So it's kind of flexible. It's less flexible than list. So basically, by default, you still list and tuple when you use Mypyc. But if you have some performance bottleneck, you can use Mypyc to kind of speed things up. And here the key thing to make this route finder faster on Mypyc is you have to kind of change the data representation to something that's more efficient with Mypyc. So for example, the graph which represents is like a nested list of tuples. Instead, we can use this vec, kind of packed array type, or 2 of them for each tuple item. Then you have the min heap to find like the next kind of shortest path to process, because it kind of goes through all the alternative paths and also takes the like lowest item to process next. The Python one uses a heap queue, standard library, because that's kind of probably the best way to do it in interpreted Python. But that's kind of not ideal for Mypyc, because we are spending time in the standard library module, which we can't speed up. So what I did is I implemented heap, my own heap, using compiled Mypyc and use like the vec I32 to kind of to hold the items. And then we have distance map, which digs from int to int, and previous map. These are kind of things that the algorithm needs. And again, like dict, we can't really make dict get item whatever fast in Mypyc because it's already optimized in Python. But what we can do like custom I32 to I32 hash table, and then compile that using Mypyc. And again, like we can use the vec I32. The vec I32 just had a lot of work for us in this example. Yeah, it's kind of, without it, we'd be kind of screwed, right? And here's the custom heap sort of kind of overview, how it works. So we just contract 2 vec. It kind of behaves mostly like list. Append looks a little different, but anyway, it's sequence. It's like a textbook implementation. I'm not gonna show you. But the amazing thing is kind of like you can implement like heap data structure. It's kind of normal Python. It runs as normal Python. When you compile, it's actually faster than the standard library kind of C thing, because this is kind of specialized to I32, whereas it's kind of generic. And similarly, this is like a dictionary implementation for like I32, like 32-bit integers. And it uses like open addressing hash map with linear probing. Again, like super basic like textbook algorithm. So I'm not gonna show you all the details, but it's relatively straightforward. And you can use like Claude code, point it to the Mypyc docs, and say like, I want to use like vec I32 to implement this thing, and it's like 2 minutes, bam, you have like this int map, and it kind of, yeah, it can do it with high degree of confidence, because, you know, it's into every intro to CS student does it. So what about performance? Like, we did this kind of pretty cool thing. I interpreted free threading is 8x improvement. Okay, pretty nice. Sequential is 3x improvement because of these kind of new data structures. That's kind of reasonable. And with free threading, we even get like 28 times faster compared to the sequential interpreter. So again, not too shabby. I'm happy with that. And okay, that kind of concludes the examples. So the common bottlenecks that we encountered, I've seen these come over and over again, work in different examples. These are kind of not just for these examples, these kind of are real. So reference contention, you can reuse references, you can use thread local objects, there are like third-party libraries can help with these data structures, but it's kind of like, there are many, you can use many objects, but it's kind of tricky. And with Mypyc, they're spending time in standard library modules is kind of the most common issue. You can use the library when it has some suitable functionality, you can use instead, like the strings and random, or you can like write your own thing and compile it. Often you can do it faster than the standard library one, and many of the standard library ones are kind of easy to replace, so actually it's not that difficult. Okay, that was my talk, and I gave you some links in case you want to learn more about this. Here's a link to the Mypyc documentation, where you get, like all the differences between Mypyc and Python and kind of all the kind of cool stuff. And then if you want to look at the code examples and see how well these things perform on your own hardware, you can just look at them, find them on GitHub. Thank you. I think we have a few minutes for questions.
Hi there, great talk. Just wanted to ask, a lot of Mypyc does sort of like these optimizations of picking sort of like the, a better integer type than using like an integer object and stuff like that. Is there any reason why for sort of like dictionaries or lists that you know are internal to a Mypyc module, you're not automatically using a vec of I32 or automatically using a more optimized implementation rather than relying strictly on the list or dict implementation and relying on the developer to opt in to this kind of like more performant option?
That's a very good question. The main reason we don't do it and probably might not do anytime soon is that because almost anything in like Python, it's kind of tries to replicate Python semantics. So everything's kind of exposed to Python. So you could have like some interpreted code accessing the list and putting like random stuff in it. And that kind of, we want to keep it kind of compatible. But if you replace list with something kind of make it look like list, it can leak into other code that then breaks when it's actually not a real list. So we kind of, yeah, that's for compatibility. We don't want to kind of break compatibility in like basic stuff, so yeah.
Hi, I was just wondering if there was a difference in like the memory footprint between like a regular Python module and versus one that was compiled with Mypyc.
Yeah, so memory footprint, so these are like function objects and type objects, or the objects like list or vec or whatever?
Like the memory object.
Okay, so generally the module is going to be probably more memory efficient when it compiles. I don't have hard data. I know that generally the import is fast. That if you compile things on Mypyc, it tends to be faster to import because all the initialization happens in C. So that's actually pretty nice. On the other hand, on macOS, it isn't necessarily faster because macOS adds some extra overhead. And then the vec types and some of the like Mypyc specific things are definitely more memory efficient than say list or even like NumPy arrays.
Okay, thank you.
Thank you, great speech. I'm JCM from Brazil. I'm not a user of Mypyc myself, but your speech is very inspiring. Thank you. And I just want to point out that why didn't you use Python 3.13? You chose, maybe you have chosen 3.14 because of the pi calculation. It's the same number.
3.13.
So it's just a joke,
yeah.
I'm sorry.
Okay.
But,
yeah.
but
Anyway, for real, like 3.13 is kind of, it's still kind of was like unstable. So it has like pretty, big single-threaded performance hit. And it's kind of, yeah, so I wouldn't recommend 3.13. 3.14 is like way, way better. You probably wait a few months. I bet like 3.15 is going to be even better. And maybe some of these issues that I complained about, maybe 3.15 fixes them. I haven't yet tried it, but there's a beta out, so maybe it might be better.
Okay, so you have already tested 3.13.
3.15. 3.13 works, but I don't recommend it because like, it's the first one, it's kind of not really big. 3.15, I think it works.
Yeah.
Just it is fixed, but I haven't played around with it, so I can't say anything about 3.15, which is coming out in like, I think, October or something.
Okay, thank you, very inspiring. Well.
Yeah, thanks for the talk. Is there any plan to support custom decorators or like custom meta classes? Especially like for the goal of integrating with bindings that already exist, because a lot of those libraries use custom meta classes.
Yeah, meta classes are kind of tricky. So we don't have any concrete plans to support like data class. Like we support like we have some custom support for data classes, and so data classes are basically fine. They're still kind of not ideal, but you can use them. For other data class types, yeah, that's kind of tricky. So we've thought about like having like plugin systems similar to Mypyc. You can lets you write plugins and you can do all sorts of kind of custom stuff. But with Mypyc, it sounds a little bit sketchy because like if the plugin has a bug, then you might generate like bad code that you might segfault or anything. So yeah, I know this is a kind of a tricky use case, and I don't really have a really good answer for that, other than you might be able to, even if the meta class or the class that you use with meta class, you might be able to compile it, you might be able to compile some of the other things that the meta class uses. So you might have some like smaller helper functions that are then used. You might still be able to get some sort of benefit, but that probably doesn't really move the needle as much.
Okay. Yeah, thank you.
Apologies for being a little selfish and asking a second question, but I noticed recently Mypyc have moved on to considering like ASD serialize and building out a lot of their sort of like starter front-end compiler infrastructure in Rust. Is the long-term goal with Mypy and Mypyc to be at the same kind of speed that TY and Firefly are kind of aiming for, or do you see self-hosting as the like one of the key goals of Mypyc, and this is going to be limited in its sort of like future applications of having things written in Rust?
Okay, let me try to unpack that. So we are replacing the parser that's written in Rust, basically because we don't want to write a parser again, because the rough parser that we are kind of wrapping, it does the job, it's high quality, so it just like code reuse. So there's no preference with Rust. We could probably do the same thing in Mypyc. Performance might be similar, it's just a lot of redundant work. And in terms of performance, yes, so we just recently released like Mypyc 2.0 and 2.1, and we have parallel type checking. It's still experimental, but it kind of works pretty well. And yeah, in some cases, we're actually faster than TY. We kind of might be competitive with Firefly. Again, in specific use cases, when you're just running like the whole, whole code base. We don't have LSP, but just straight line, type checking speed is actually, can be pretty good. But it depends on your use case. And you're kind of, I'm not saying like, I'm not going to claim that we are faster, but I'm saying like in some use cases, we are kind of already significantly faster and kind of pretty happy about that. This is still like almost entirely everything happens in Python. So we have used a rough bit, but you only use like 5% of CPU in Rust.